Okay, so what is the scoping rule? The scoping rule itself is pretty simple. So what the project description says is that if you have a code like this,
Will you please move the paper?
pardon?
Will you please move the paper?
Oh, okay. Which one is the zoom out button? I think it's wrong. Okay, this is officially wrong. The zoom in, zoom out does not work. So what do we do? It's just zoom same. Yes, actually, yeah, that is good. Let's do it here, then I have to rewrite it. And so test set public A, then it has a private variable that is C, and then it had one nested loop, a nested scope, sorry, which is public B, and it had C equals B, and then it had another nested scope, private B, and it had D equals A, right? So this was our code. So this is, if you look at the grammar, this is correct grammar. This will parse very well. But you shouldn't first parse everything, see if there is a syntax error or not, and then try to go back and do scoping. That will mess things up. So what you do is, as you parse, you know that when you came here, this is tested scoping. Whenever you have a variable declaration, you have your stat, right? Symbol table. So in the symbol table, you have a symbol table item, right? What is that item? That item has maybe a character pointer, which is name, a character pointer, which is scope, and you can have an integer, which is permission. All this is already in the notes that I uploaded as dissertation slides. I'm just trying to explain. So if you have that, so that is your symbol table entry, one of the entries. Then using that entry, you make a symbol table stack, right? You make a stack. Now once you do that, then what you do is every time you come to a definition or declaration, so public A, what you do is, if you have this public A in the stack, you do this. You have A, that is the name is A, scope is public, No, sorry. The scope is tested. Tested? Scope is tested, and the number, permission, 1 or 0. Let's say for public it's 1, private it's 0. Let's assume. So you keep it 1. Right? So that's your first entry in the symbol table. Then you come here, you see private C. So if it's private C, then you have another entry, C tested 0, right? When you go inside this scope, nested scope, don't have to do anything to the stack as of yet. You come inside nested scope, you see that this is public B, another declaration. You have another item. So name B, scope is nested, and 1, right? You have this symbol.
Sorry, what was the number? 1 0.
Permission. 1 is for public, 0 is for private, right? So now you have an assignment. Now the moment you have an assignment, you know that you have to do scope resolution. So the moment you see an assignment, while you are parsing, you do the scope resolution. Right? That will make things easy. So while you are parsing, you see that C. Now, what is the scope of C? How do you know? You search the symbol table. So you search from the bottom up. You search here first, right? You search here and you search by name. So you see that name is B. No, it didn't match. Then you go up. You don't push or pop anything from the stack, right? Don't push or pop. You just search. So you search name B, it doesn't match. Name C, it matches. You see that the scope is tested, right? If scope was nested, then no problem, right? You don't have any problem. But scope is tested. If scope is tested, you have to see whether it is public or private. So then you check this number 0. You see that this is private. So you cannot use this C inside this tested or inside this nested scope. You cannot use that C. So what you do is you keep on searching. So you found C, but this is private, and the scope is different from nested, right? Because you are taking an assignment and your current scope is nested. So you should keep a variable called current scope. You should always keep a variable called current scope. Whenever you parse a new scope, you update that variable. So now what you do is you check the name first, C, you found C, you match the scope. Is this my current scope? You see, no, this is not my current scope. If it's not my current scope, I'll check whether this is public or private. Right? You saw that this is private, so I cannot use the C. So what you do, you continue searching. If this was public, you would stop. You would say that I found the scope for C, and the scope will be tested. Right? If it's not private, you continue searching. Now you continued searching, you didn't find any C. So you make the scope of C as question mark. You don't know which C to use. Right? So that is how your logic should go. Now if you go further, you finish the scope. Right? Oh no, we have to also do B. Sorry, we have to also do B. So you check B, you find B here. You check the scope of B, it's nested, its current scope, doesn't matter, it matches with the current scope, doesn't matter permission is 1 or 0, you have the variable. Right? Doesn't matter because you are in the same scope. So here you immediately can print, you don't even have to finish parsing. You immediately can print that this is question mark C equals I think some format colon or something like colon. Question mark dot C and nested dot B. Right? Immediately you can print, or you can keep the printing for the end also. Because if there is a syntax error, then you don't need to print anything. You just print syntax error in the file. right? So you do this. Then you come here. Now what happens when you are out of scope of nested? What should you do?
Pop the distance here from the stack.
Yes. So what you do is you go to the stack and pop all the variables that are of nested scope. Now if you follow this rule, you will never have a case that this is nested, this is tested, and you have another variable called nested here. You will never have this case. The moment you get out of scope, if you pop all the variables that are for nested scope, then you'll never have that case that scopes are intermingled. You won't have. You'll have a continuous block of same scope, right? So you'll never have this. So now what you do is you pop. So if you pop, this goes away. Do not pop anything other than variables that have the same scope, nested scope, current scope, right? Now when you go out of scope, what you do is you have to revert back current scope. You have to make current scope as tested. How do you do that? Again, go back to the symbol table, take the first variable, whatever is the scope of that variable, that becomes your current scope. Yes.
So when we have the nested scope be on the stack, then the current scope would be nested, right?
Yes.
Okay.
So whatever is the last element of the stack, the scope of that element is your current scope. So that's why when you pop, or when you go out of scope, you have to update your current scope, right? You have to update your current scope. The way to update your current scope is that you pop whatever is in the stack. After you have popped, take the last element that was inserted in the stack. The scope of that element is your current scope. Then we go to the next one. You see that there is another scope, nested 2, and you come here. You see, so you make current scope as nested 2, right? So you come here, you see there is a private variable d. So you have again this d nested 2 0. Right? Now you have an assignment d equals a. What do? You go back, check, search the symbol table. You see that there is a variable t. Its scope matches my current scope, so does not matter whether permission is 0 or 1. I write, okay, this is nested 2 dot d equals. I get to a, search, d no, c no, a, yes. So a has a scope of tested. It's different from my current scope. So if it's different, I will check the next number. Is it public or private? I see it's public, so I can write it here. So then what you do is you say tested dot a. That's it. So that is how you can operate the symbol table. And once you have that, once you do scoping alongside parsing, then the entire project becomes very easy. Now the only difficulty that you will have is building a stack, right? So you'll have problems using pointers and all those things. You'll have segmentation faults. You'll have to be very careful about how you implement the stack. Right. So what I would suggest is first finish implementing a stack with any kind of structure as item, and then do some testing on the stack. Do some testing on the stack. If the stack works fine, then your entire project boils down to just implementing this logic. This logic is easy. Right? So do you have any questions?
Why are we using a character for the
Because it can be a string. It can be a string or it can be just a just a what do you call it, alphabet. Any other questions?
If there's an error in the code, so we just stop right there. We don't need to parse.
Yes, if there is a syntax error, you stop, you don't print anything, just print in the entire output file, just print syntax error. That's it. Any other questions? If no, then we'll go back to our discussion. Yeah, on implicit polymorphism. That's what we were discussing. Okay, so we were talking about implicit polymorphism, and we said that even if we do not declare types of a given variable, we can still, from how the code is written, we can still find out the type. And we can not only find out the type, we can assign basic types. We can find out what types are equal, and we can also find out if there is an error, if there is a type error, right? All this without declaring any kind of variables, right? Without declaring it. So we were thinking about, or we took the example of functional programming languages like MATLAB or Python or others. We'll see. Lambda calculus is another way of functional programming language, which we'll discuss later. So Hindley-Milner type checking is a general type inference approach. It infers the types of constructs that are not explicitly declared by the examples that we saw. It has two things. It has constraints and it has a unification methodology. So last class what we did was we discussed about the constraints. Right? So let's revisit those constraints because those are important. You have to remember those. If you don't remember the constraints, then you won't be able to do type checking. So let's. So these are the constraints for the basic types. So any integer 0, 1, 2, -1, -2 will have the type int for them. Any real number 0.1, 2.2 will give the type real. Any booleans true or false will give the type boolean. Any string will give the type string. So these are the first basic types constraint. Right. Then we have constraints for operators. First we consider relational operators. So which are what? Basically a greater than, less than, equal to, and so on. Now for each of these operators, what we'll do is we'll try to represent them in the form of a tree. And we'll see why it is important to represent them in the form of a tree. Because if you do that, then later type inference becomes a lot easier. And you can also implement it in a computing system. So let's see. So how will we represent a relational operator? A relational operator the operator itself has to be the root. And we assign the type T1 to that operator. Then the left child is A, the right child is B. And each of them have different types for now. Now what are the constraints? The constraints are T1 have to be Boolean. So if OP is a relational operator, which means less than equal to, greater than equal to, or not equal to, or double equal, means both are same. Then the constraint is that the output of OP will be Boolean. T1 has to be Boolean, and T2 has to be equal to T3. These two types has to be equal. So you have to remember this rule. So OP, the moment you see a relational operator, then you have this picture in mind, that there is a tree, OP is the root, A and B are the left and right child. So what we will have is the type of OP should be Boolean, A and B should have the same type. And you have to remember this. Then we have arithmetic operators, plus, minus, equal to. Kind of similar. So again you have OP as the root node, A and B as the left and right child. If OP is plus, minus, multiplication, divide, then the constraints are T1 equals T2 equals T3. So these are different constraints. As opposed to relational operators, T1 is not Boolean. For arithmetic operators, T1, T2, T3 all are the same. They might be Boolean, they might be integer, float, we don't know, strings, right? We don't know, but just the type should be same. Then we have the array access operator, A, square brackets, B. So how we represent that? We take that square bracket and make it the root. It's kind of weird. This example is kind of weird, this root. So you take the square bracket and make it the type root, or make it the root node, and also assign a type T1 to it. Now square brackets are not any variable, so how can I assign type? Let's assume that we can assign type. Then we have A and B as left and right child. So if you see this tree is very similar to the relational operators and arithmetic operators, right? Very similar. So basically what is happening is that the square brackets, we are considering them as one type of operator. It's a type of operator, it's called an array operator. So what is the output of an array operator? There is no specific output, but the type T1 of the array operator, or whatever may be the type T1, it can be integer, character, string, whatever may be the type T1. T2 has to be array of T1. Right. So if you have A square bracket B, then what happens? You get one element of that array. Right. So that element can have any type. So type of that element is T1, and that is what the array operator represents. The type of that element. So A becomes array of that type, so it's an array of T1, and then T3 has to be int. These are the constraints of the array operator. T3 has to be int. Then we have function application. So now there are two concepts: function application and function definition. Right? These are two separate concepts as with respect to type discussions. When we are discussing type, the application and declaration are two separate concepts. What is declaration? Declaration is you are defining a function. You are saying, okay, this is a function and this is the body of the function. That is declaration. As opposed to application, where you are actually using that function to set some variables. Say C equals fun x1, x2, x3. Right? So application and declaration are two different things. So the way we represent application is this, that if we have foo x1, x2, x3, then what we have is we make a root node, which is basically the return type. Right? We make a root node called apply, and make the type of that apply root node as R. Then we say that the leftmost child is foo, the function name, and we also associate a type with that function name, and that type is it. Then we have all the input variables as children. So x1, x2, x3 up to xk, and each of those children have the type have types associated with them. So x1 has type t1, x2 has type t2, and so on. That is how we represent a function application. Now we come to the constraints. The constraints are f is this. So which means f takes in f is a function of type t1, t2 up to tk, and it has a return value of r. So if you remember at the last class how we represented function, is much further back here. So we represent function like this, right? So whatever is the argument, we take it in parentheses, and then we have a right arrow, and then we write the type. So same here. Same way here. So whatever are the arguments, we put it inside parentheses, then right arrow, the return type R. That is function application, and that is the only constraint for function application. Now we do go to function definition. So function definition has to have that syntax that you have fun, the keyword fun, then foo x1, x2 up to xk, and equals to some expression. So expressions can be if x is greater less than y, then x else y, like a mathematical expression which you can actually evaluate, right? So now how do we represent this definition? So we have to have a root node which is called fun. We don't give a type. We don't give a type to that root node. Then that root node has the left child which is foo x1, x2, xk, and it has types like this. That foo is a type of f. X1, x2, xk has all the types t1, t2, t3. Then we have the right node which is expression, and that expression has a type e. Right? The expression has a type e. Now what are the constraints? The constraints here is a little bit different from function application. So what we say is that whatever type the expression evaluation returns, that is the type return type of function. That is what we say, right? That is the constraint. Whatever the type returned by expression, so you compute the expression, it returns some value. The type of that value goes to the return type of f. That is the constraint. Now we have expression. So how to evaluate the type of an expression? So we look at that. So there is this if expression. How do we evaluate the type of if expression? First of all, how do we write if expression? In here we write if expression as like this. So if there is a condition that x less than y or something like that, if condition, then you evaluate expression 1, else you evaluate expression 2. That's what you do, right? In case of a if. So how do you do that? How do you represent it? So you have a if root node and give it a type t4. You have the condition as the leftmost child, give it a type t1. Then you have expression 1 as one child, t2 is its type, and expression 2 as another child, t3 is its type. Now what are the constraints? The first constraint is t1 has to be Boolean. Whatever the condition outputs, it has to be Boolean. Right? And t2 equals t3 equals t4. So which means that expression 1 should return the same type as expression 2, and the output of it should have the same type as expression 1 or 2. So that is the constraint. So these are all the constraints that you have for Hindley-Milner type checker or type inferences engine. Right. So do you remember all of them? Let's go again and just refresh, because these are very important. So again, very quickly, type constraints, we know integers, real numbers, boolean, strings. Then we have relational operators, less than, equal to, greater than, those things. So what is the relational operator type? T1 has to be boolean and A has to be equal to B. So type of A has to be equal to type of B, T1, T2. So A less than B, type of A has to be equal to type of B. Then if you have arithmetic operator, same representation in terms of tree, only difference is all the types have to be the same, even the output of OP. Then we have array access operator. This one was kind of weird. The square brackets, we have a type T1 and we say that T2 is array of T1. So basically A becomes array of type T1 and B has to be int. So this is for operators. Function, application and declaration were two different things. For application, what we did, we have a root node, we call it apply, and we give it the return type R. We have a node foo with the return type F, and each of its arguments. Constraints are F has to be T1, T2, Tk, right arrow R. Right. Function definition. The only text, the representation is very weird. But the only constraint is that the return type of function foo has to be whatever the expression returns, and whatever is the type of that expression. That is the only constraint. Then we went to if expression. If expression, the only the two constraints for if expression. The condition has to have a type boolean, and all the types of the two expressions that are there for if, that has to be the same, and the output of if also has to be the same type. Right? Those are all the constraints. Now we go into type unification. So what is the purpose of type unification? Type unification is the process by which constraints are propagated. So why would you want to propagate constraints? In general, if you see any code, the most basic thing that you can do is give every variable, every function, every expression its own type. Right? Just give it its own type. All variables have different types, all functions have different types, all if expressions have different types. And you are done. But is that useful? If you just give random types to everybody, every variable, why is that not useful?
Constraints, types of equal.
We need to check whether types are equal. Why do we need to check whether types are equal again? Because we want to understand the semantics of a code. If we do not equate types, then we don't know whether we can do A equals B or not. A has a different type, B has a different type. Can we do A equals B? We don't know. So we want to do A equals B. We want to do A plus B, right? So if we apply all variables have different types, then we don't know whether we can do A plus B, whether we can do A equals B or not. We don't know. So that's why we need to unify. We need to unify and see which variables have the same type, which types are equivalent. We need to do that. Now the only way to do that is use the constraints, because see, the constraints say has a way to determine the types are equal or not. The constraints give us a way to determine equivalency between types. So we have to propagate the constraints. So that process is called type unification. So do you now understand the idea of type unification? Why do we need type unification? Do you have any doubts? Anybody has any doubts? Should I explain it again? Okay. So let's go ahead and see how do we do type unification. So what you do is you start from the top of the tree. So whenever you see a code, you can use those tree representations, right? You can take one line, represent it as a tree, then you go to one node, expand it, again represent it as a tree, and so on. So for every code, you can represent the entire code using a type tree. So you start from the top of the tree. Every time you see a construct with unconstrained types, create a new type. the description might seem confusing. We'll see an example and that will make it clear. So every time you see a construct with unconstrained types, create a new type. If a construct is found to have type T1 and also have type T2, then T1 and T2 must be of same type. What does it say? I mean, in words it's very confusing, but the idea is very simple. So what you do is if you see that there is a variable and none of the constraints apply, right? You have all those constraints. None of the constraints apply. If none of the constraints apply, just give it a new type, right? Just give it a new type. Now you continue with the tree. Now while you are doing this, you found out that the same variable had another type, T2. So you first gave that variable type T1 because it was unconstrained. Then that variable was used in some other place. Whether it was constrained or unconstrained, doesn't matter, it got a type T2. So if two variables have two different types, you can unify, unless there is no conflict. Like one is int, one is float, then you cannot unify. Okay. But if these are two general types, then just say that T1 and T2 are the same. Okay. So let's see an example, it will become much clearer. So this, let's say we have this function, foo a, b, c, then c equals a, b. Now before going here, let's do it on the board first. So before even checking the type, what does this mean? What is B? What should be B? B has to be an int. What is A?
It's an array.
A is an array of some type. We don't know what it is, but let's say A is an array. What is C?
Function.
C is a function, and so is foo, right? Now the first step is we see that this is the function declaration. So if this is a function declaration, then how do we represent it? So we go back, we see that, okay, how do we represent function declaration? Function definition, basically. So this is how we represent function definition. So what we have a root node, we call it fun, we don't give a type to it. Then we have foo, and we have some arguments. So foo's type is a, right? And we have some arguments. So now let's go to the specific arguments that are available. A, B, and C, right? So we have A, B, C. So give it T1, T2, T3, right? And then we have expression. Give it type T4, right? Now this expression is what?
Function.
Is it a declaration or application? What is that expression? Is that a function declaration or is it an application?
Application.
It's an application. So if it's an application, you go back to that constraint slides where we did function application. So how did we do function application? This is how we did function application. So you have a root node which is called apply. You give it a type, let's say T4. There it's R, but it can be T4. Then the function was this, right? function was C A B, this one, right? So you have this node C and you have a return type F2, let's say, because if we already used. So we are giving just new types. Then you have to one input, right? One input. Now what is that input? Array. So let's go to yes.
So when you put C, that's also when you do it F2, but didn't you already mark it as T3?
We'll come to that. Yes, exactly. We marked it as T3. So at this point, what we can do is we can unify. So that is the type unification. If we see T3, F2, we can unify. But we'll come to that a little bit later. We won't do unification right now. Right? Okay. So now the next thing is array. So let's go to array. Array. So how do we represent array? We have this node and we give it T5, right? We give T5 and then we have here A, we give it T6 and here we have B, we give it T7. That is the entire representation of the code that we have written, right? Now we apply the type inference. That's the same thing, right? Instead of giving T1, T2, T5, T6, that here I just gave numbers. So now what you do is you have this array, or not array, you have a table. So here table means what? You have to give foo some type, you have to give A, B and C some type, right? And there are other types which are unresolved. Say 1, 2, 3, 4, 5, 6. These are all unresolved. Right? So now let's resolve one by one. So how do you create this table again? You take all the function names, foo, you write those. You take all the variable names A, B, C, you write those. You have an entry in the table. And then all the types that are not resolved, 1, 2, 3, 4, 5, 6, you keep it there. Now you have to slowly resolve this type. So how do you do that? You start from the first. Is it starting on the bottom? The top of the tree. Okay. So now, once you go to the top of the tree, you don't need any type resolution here. You come to this one. You have given T1, T2, T3 to ABC. Put it there. Put it into the table. T1, T2, T3. Now, if you do that, then you can also say that T1, T2, T3 goes to T4. But there is some. There's confusion because I made them 3, 4, and I'm confusing it with the T3s and T4s. So okay, so there's 1, 2, 3, 4, 5, 6. These are different from T1, T2, T3, T4. In my mind, I was confusing them. Anyways, so that T4 there is F here. So let's write this as T4. Let's not follow the slides. That will confuse. So you have this table. You have to have foo here, A, B, C, and all the unresolved types. So you have to have T1, T2, T3, T4, T5, T6, T7, T8, and T9. Now we go to the top of the tree. That root node doesn't need any type. So you come to this node. Now you see that this T4, T1, T2, T3. So what you do is, okay, A is T1, B is T2, C is T3, and what is foo? Foo has to be, it has to take the arguments T1, T2, T3, and return type is T4. By just executing this node, you understood that is what it should be, right? That's what you understood. Now you come to this function application. No, this function declaration. You try to understand the constraint of the function declaration. What is the constraint of the function declaration? Function definition or declaration says the constraint is that if that is the case, that T4, T1, T2, T3 an expression, then this T4 has to be whatever expression returns. Right? That's what it should be. So now what you then what happens is that whatever apply returns, that should be T4. Applying that constraint. Do you understand this? If you apply this constraint, what does this constraint say? Constraint says that f is T1, T2, Tk, and it returns whatever that expression returns. So what is the expression in our case? The expression is this node, and this is T5. This returns T5. So T4 must be equal to T5. Do you understand this? Now you can keep any of them. Either you keep T5 or you keep T4, does not matter. Right? Let's say we keep T4. If we keep T4, then what we know is that this application, this applied, this has to be T4. This cannot be T5. Right? Understand why it became T4? Now you're done with this node. You come to this node. So you know that, okay, apply has to be T4. Now this is function application. So let's go and understand the constraint of function application. Function application says that the constraint should be, this one has to be a function. T6 has to be a function, right? So T6 has to be a function, and of what type? It has to take that T1, T2, Tk, so T7, it has to take T7 as input, and it has to return the value R, which is T4. It has to return T4, right? So what does T6 become? T6 becomes a function which takes T7 as input and it returns T4. That is what is T6, right? Now you know, you see that you have given C, the same variable. See, C has T3 and C here also has T6. So what you can do is you can replace T3 by T6, which is T7 goes to T4. Every occurrence of T3 you can, so T3 has to be same, so T3 you can replace by this, goes to T4. what was this? T4. It was T4. Right. So after evaluating this node, after evaluating this node, we found out that T6 was T7 goes to T4. Then we came to this. We wanted to evaluate this node. This node we see that this we have C again. So T6 has to be equal to T3. Right? So and T6 we know is T7 goes to T4. So we replace all T6 and T3 by the same expression or same type. So we are done with this node. Now let's evaluate this node. So what does this node say? This node is an array operator. So let's go to array operator. Array, yes. So if it's an array operator, then we know T7 has a type, some type. We don't know yet what is its type. But T8 yes. So T8 has to be an array of T7, right? So you say T8 is an array of T7, and it's an array of T7, right? And we know that T9 has to be an int. So T9 is an int. So after applying this, after evaluating this root node, we found out that these two have to be changed. So T8 has to be array of T7, T9 has to be an array of int. It has to be type of int, right? Then we come here. So T8 we know is array of T7. We see that A is same as T1, right? So we replace A. So T1 becomes array of T7. And that one also becomes array of T7. That's it. We don't have anything else. Right? We don't have anything else.
Wouldn't you fill the T1 box?
Oh yes, yes. We can fill the T1 box, which is array of T7. Right? So that is where we stop because we don't have any other root nodes to evaluate. So now what will happen is that this T7, T4 and T2, we don't really know what they are. Oh no, there is one more. We didn't evaluate this node. This node says B is an int. So B is same as T2. So T2 becomes an int. Now we are done. So by just going from top down, we found out that these are the things that we can argue about. The other things we don't know. So T4 is a generic type, T5 is a generic, no, T5 do we have anything? No.
It used to be applied.
We used to be what?
Apply.
Oh, it used to be applied. Okay, so that we didn't update here. T5 has to be T4. Yes. We didn't update. Okay, so we don't have any general term for T4. We don't have any general term for T7. So these are types. These are type variables in our case. So what we have finally is that foo. What is the type of foo? Foo is an array. So it takes an array of what is that? T7. Okay, it's an array of T7. Then it has to be int. this one, then C is what T3 is. It takes T7, outputs T4. And its return value is T4. So we have foo as this one, then we have A as array of T7, then we have B as int, and we have C as T7 goes to T4. Okay. By looking at this definition, that is what we can say. Any doubts? Yes.
Can you explain again how you get that C parenthesize T7 to T4?
Which one?
C.
C as T7 to, okay. So here we have apply, right? Apply's type is T4. Now let's look at the apply constraints. Oh, you don't have it there. Let's look at the constraints of apply. Yes, here. Okay, so we said that the rightmost child has to be foo F, right? So we have T6, that is C here. So C has to be that foo. And we have some arguments. T7 is the only argument, which is the array operator. Fine. What is the constraint? The constraint says that F has to be T1, T2, Tk to R, right? And what is R? R is the type of apply. So that's why F is T6. T6 is basically T7. It takes T7 as input, right? T1, T2, Tk. Only one we have had here. We have only one input argument. So it has to take T7 as input, and it has to return whatever is the type of apply. So that's why C became T7 returns T4.
Okay.
Right. Do you have any other doubts? Yes.
Why there's T4 function full? Because in the function definition slide, it's different. It's F and E. It doesn't have to be same as the five.
Which one?
The function definition.
Function definition. Yes.
See, F above the function folder is F, and the
Yes.
output is E. It's different, but on the board it's both T4.
Okay. So T4 is the return type of foo. I mean, okay. So foo's type is not T4.
Oh.
Foo's type is not T4. Foo's type is this. This entire thing. It returns T4. So any doubts? Any more doubts? I think your project 3 will involve type checking. So you have to understand Hindley-Milner very well. Right? So this example is shown in the slides, but it's a little bit different because we have used different names, but the result is the same. So what you do here, so we have defined the names like that. So def has a type 1, then apply has a type 2, 3, 4, 5, 6, and we have foo ABC. So when we evaluate the first root node, we say that we come to that conclusion that A, B, C are T1, T2, T3. Then we do the apply node. We evaluate the foo node. Right? When we evaluate foo node, we see T1, T2, T3 to T4. That's what we argue. Then we check the apply node. The apply node says that the type has to be T4. Why? Because you apply the rule for function definition. So expression has to be the same type as the return type of foo. Then you go to the apply node. The apply node says I need to update this slide. This slide is not really how it should be. Whatever we discuss here is how it should be, because you should go from top down, evaluate each of the nodes. So I will update this. This is slightly wrong, but the result is same. The result is same. Instead of array of T5, we have array of T7. Does not matter because T5 and T7 are all generic types, right? So you can as well equate T7 with T5 and T4 remains T4, right? So since those are generic type, does not matter. So we have same, it's an array of T5, you take int as another variable, then T5 goes to T4, and finally the return type is T4. Same here. Okay, so you can now go ahead and do some examples of this. I don't have anything else planned for today. So if you do not have any questions regarding assignments yeah, if you don't have any questions regarding assignments or Hindley Miller, we should stop here, because the next topic we are discussing will be runtime execution. It's a lot difficult. It's a very difficult topic to understand. So we will start afresh next week. First midterm we are also doing that. So maybe by next week, by end of next week, you will.
All functional applications expression.
Yes.
Then